till Thursday,
Friday.
right?
Good. More people are here today. I was worried last week. No one showed up. Okay, so I'm looking at the schedule, and I was going to go on today. I'm going to start. Pretty sure I'll start talking about quantum mechanics because I want to give you guys some review time before the next test. So, and I can spend a class period doing that as well. But anyways, moving on. Anybody have any questions about anything before we start here? Okay, so we're going to talk about standard states. So if you remember enthalpy H, it's path independent, also known as a exact differential, also known as a mother function. So all these things mean the same thing. So path independent. And because of that, you can pick a reference point and then relate everything to the reference point and make calculations much, much easier. And that reference point that we picked are the standard states. And what's interesting about standard states is that when, with the end of the Cold War, we started collaborating scientifically with the Russians. And it turned out we had different standard states. And truth be told, the Russian standard states made more sense. And what did we do? Did we adopt the Russian standard states? Of course not. We flexed our American muscle and said, you're doing our standard states. And they're using our standard states now. I don't know what their temperature is, but Russians use pressure of 1 bar. 1 bar is 100 kilopascals. And we use 1 atmosphere, which is 101.3 kilopascals. So it's, like I said, theirs actually makes more sense. It's more engineered, but hey, America. So, all right, so standard states. Here are the standard states for a gas. It's a pure gas at a pressure of 1 atmosphere. Liquid or solid, you select, well, for the standard state for a liquid, it's the pure substance at its most stable form at a pressure of 1 atmosphere and a temperature usually 25 degrees Celsius. So, for instance, elements can have several different states. Take carbon. Carbon can be graphite, it can be diamonds, it can be nanotubes, it can be fullerenes. All carbon. And we have to pick one. Which one do we pick? Graphite. Pick graphite. That's the most stable. Oxygen can be oxygen radical, can be O radical, it can be O2, it can be ozone O3. Which one do we pick for oxygen? O2. So usually and that's typically the most, stable of everything. So then the enthalpy change, standard enthalpy change, it's when there's a process or reaction when everything is in their standard states. And also enthalpy of formation. We were doing this last class with Hess's law, did the enthalpy of formation of propane. Pure compound definition, obviously we change the enthalpy when 1 mole of the compound is formed from its constituent elements in their standard states. And elements, so the enthalpy of formation of a pure element in standard state is 0. So it tells you something about enthalpy H. Enthalpy H is a relative scale. So we pick zeros and compare it to other scales. So temperature. Temperature, we have relative scales and we have absolute scales. So Kelvin, that's an absolute scale. 0 Kelvin means you can't go below 0 Kelvin. You can't get slower than not moving. Celsius is a relative scale. 0 Celsius is when water freezes at 1 atmosphere. So that's our 0. So we're picking our zeros. So there is no absolute enthalpy. Enthalpy is always related to something else. It's always related. And why did we pick these as the zeros? It makes the math easier. So we always pick things to make the math, or at least attempt to make math easy. So here's lots of data. You will never have to memorize data, and you'll always be given it to you. And notice, like right there, here's oxygen. There's a couple different states. The 0 is O2, so there are some zeros here. So like here's chlorine. There's chlorine radical. This plain old Cl, and Cl2 is 0 there. So we pick our zeros. And I'll get to this in a second. The equation, so the standard, and this degree sign. When you see that degree sign there, that means standard. So when you have the degree sign, that means the standard enthalpy change for a reaction is the sum of the moles of products enthalpy for a formation of products minus the moles of reactants, standard enthalpy of formation of reactants. So let's do this one here. So use the standard enthalpy as a formation to determine the standard enthalpy of reaction for this reaction. So we have 4 ammonias plus 5 oxygens makes 4 nitrogen monoxides and 6 waters. So we apply this equation, and the delta H0 reaction is going to be products minus the reactants for so I made sure to put gas for water because there's one for gas and one for liquid. So now we have to put in the numbers, and notice the heat of formation of oxygen, it's 0. So we don't have to put that with it. Now we just have to put the numbers in. So heat of formation of nitrogen monoxide. So we gotta look for nitrogen monoxide. It's right here. 91.3. 4 times 91.3 plus 6. And it'll be water, and it's gas. So minus 241.8. Oops, 241.8. And notice that there's gas and liquid. Make sure you have the right state. If you have the wrong state, you have the wrong energy, you get the wrong answer. Minus 4 heat of formation of ammonia. So it's nitrogen again. Minus 45.9. And oxygen 0. So you plug it on, I already put the answer there. This is equal to minus 902, and the units are kilojoules per mole. Okay. And I don't know if I told you about the sums. When you have a sigma, capital sigma, it's like if you have this series here, like say inverse n. So n equals 1 to 5 inverse n. This is, you just put in 1 plus 2 plus 3 plus 4 plus 5. This is the sigma means sum. And if you have a capital pi, that's capital pi. This is known as a geometric series. So this is an arithmetic series. The top one is a geometric series. So if you haven't seen this before for mathematical notation, I guess I should have started with that before I started applying the formula. So when you see these sigmas, it's the sum. So when you do that, the sum, and N of P, this is moles of products. So 4, formation of nitrogen monoxide, 6, formation of water, 4, formation of ammonia, 5, formation of oxygen. Oxygen is an element, it's 0. So remember, we picked that as our reference point, and then plug in the numbers, and minus 902. Questions on how to do this? This is usually pretty easy. I mean, this is, I know this sounds like, here I am, I sound like a scientist. This is actually really spectacular, because now you don't have to do the experiment. We have the relative energies, you can go look them up, you can carry it out, and you can figure out what the energy is. And later on next semester, you'll find out that you can include an equilibrium in with this too. So from all these data, you can figure out if the reaction, if it's exothermic, endothermic, if it's going to go, if it's not going to go, and what it's going to be like at the end. So that's one of the amazing things about chemistry, is that we know how to do all these things based off of the energy. So I think I said this before, a day in the library will save you a month in a laboratory. Can you imagine what the world would be like if we didn't have standard states? What I mean by that is every time you did something, like, we do things and we don't even think about it. You go to the doctor's office and they take blood and they say, oh, you have this, and they look at the levels there. When you make something, you're making soap. If you're making beer, you're making wine. You take the materials and you test it to see if it was in the right parameters. And then all these are based off of something that you've taken standardized of. Can you imagine what it would be like if every single time someone's like, well, we found this, but we don't know what this means, so we're going to have to test it and figure it out. I mean, someone's done this work for us already, and it's right there, and now you just have to know how to use it. And that's what you're doing here, is you're figuring out how to use it. Okay, let's see if you can figure out how to use this. So this is the thermite reaction. So aluminum plus iron oxide makes aluminum oxide, also known as sapphire, and iron. And I guess, well, thermite would actually be iron liquid. Let's see if you can figure this out. Has anyone ever heard of the Hindenburg before? It was a Zeppelin that exploded. The Zeppelin had hydrogen instead of helium. Why did it have hydrogen instead of helium? Because we in the United States, we hoarded all the world's supply of helium. And then, so the Germans used hydrogen, and then they had rusty paint with aluminum, and a spark started the thermite reaction, which caught the whole thing on fire, plus the hydrogen made it explode. So if you ever want to look at the Hindenburg. Of course, we tend not to use blimps or Zeppelins anymore. And why iron oxide paint? Because it's cheap. It's red. You ever seen, like, you ever wonder why there's lots of red barns? You ever go to the mainland, you're like, oh, there's a red barn. Oh, another red barn. Why are there a lot of red barns? Because red's a really cheap color to paint things with. Nothing special. Kind of like why we paint the roads white, at least the lines on the road white. Well, it's easy to see lighter colors and it's cheap. Anybody getting stuck? Fe2O3 is different than O3. O3 is just ozone. Fe2O3 is rust. So that's well, that's why I gave them.
Oh. So how would I normally find that out?
Look in the table. There's data in the back of the book.
Oh, well, this is another.
Yeah. The list I gave you before is not a complete list. There's a more complete list in the back of the book, and there's even more complete list in other publications, like the Handbook of Chemistry and Physics has got a lot of them, and Perry's Handbook for Chemical Engineers has a whole lot of them too. So it's the products, right side of the product. It's going to be times 1 plus 2 these are the products. And that's the product. So the ends, it's 1 and 2. 1, 2. And these are the reactants. So minus the reactants. Here are the reactants. 2 and 1. And then just put in the numbers. There's no O3, just Fe2O3. Okay. Al2O3 Fe2O3. Okay. You want to know. Yeah. So you want to know what is the formation of what is that? This is if you take iron, if you 2 irons plus if you do this, so like in this case, this is iron, this is oxygen, and it's exothermic. It's very reactive, and then it forms this, and then you do a heat reaction divided by 2, and you do that.
Okay.
I give you the equation.
I mean, like the one that you just wrote up.
Yeah.
Did you read this?
The problem you'd be given the equation on a sheet of paper,
So you need to figure out.
and then you need to figure out a reaction with the equation. I mean, Yes, you need to memorize. All right, to prove a point, I'm going to go grab the handbook of chemistry and physics. I'll be right back. All right, just to prove a point, this is the 54th edition of the Handbook of Chemistry and Physics. I bought this. This is my own copy. I bought this at a book sale for like $1. So inside of it has a bunch of stuff. I guess you haven't. Okay. There's a lot of integrals. So like if you ever, I mean, if you're doing math, here is the integral. Oh, geez. That's a crazy one. I guess no one's here in advanced calculus. So they have all the ones. Oh, here's the trig ones. Like the integral of dx over a constant squared plus x squared equals 1 over the constant times the arctangent of x over the constant. I mean, oh well, but I mean, crazy stuff here. So there are physical constants in here, like molecular weight, solubility in hot water, solubility in cold water, and solubility in other solvents. Like, it turns out that cobalt-3 sulfate is soluble in sulfuric acid. Who would have known? Well, look it up here. And density, table of isotopes, physical constants. Oh yeah, even here, no, they don't have that. Eventually here you'll find thermo stuff. Formula index. Oh, here we go. Values of chemical and thermodynamic properties. So yes, I have them all right here. So right here you can look them up. Or you can look online, but I mean this list here. Oh, it's pretty much done. Oh, it goes through the elements. So, I mean, so uranium pentachloride, the heat of formation of uranium pentachloride is minus 262.1 kilojoules per mole. So you can look all this stuff up in here. So if someone's asking, where do you get those numbers? And the other thing is, let me get my iPad. So if you're wondering exactly what this is, do we have iron? Oh yeah, here's a thermite reaction. So this is the one that we did. So here's a thermite reaction right here. And see the red stuff, that's iron oxide. You mixed up aluminum powder and iron oxide. And you have activation energy in the form of a sparkler. And now you have a thermite reaction right there. It's very explosive. And it makes iron. Right, do I have a formation? Let me see what aluminum's reaction is. This is just something that's all the different elements. What are they doing? Aluminum. Oh, I didn't know that gallium and mercury are. Oh, wow. That's kind of cool. So no mercury on aircraft. Oh, that would be bad if you broke a mercury thermometer, and that's what happened to the whole of the aircraft. That's pretty cool. Do I have... I'm just trying to see if there's a formation. Okay, here's one. This is the formation of sodium chloride. So there's sodium metal, and here is chlorine gas. So sodium metal is an element, and chlorine gas, and now that form, that is sodium chloride salt. And this is a guy, whatever, Theodore Gray. He's completely insane, by the way. And he has some eggs there. He's salting the eggs. So this is an example of, this would be the heat of formation, so of sodium chloride, salt. So here, there's sodium metal, there's chlorine gas, and then there's the exothermic reaction to form sodium chloride. So then the heat of formation of sodium chloride, do they have that in that list? Let me look. NaCl, yes, it's minus 411.2. So right, that's that reaction there, minus 411.2. So someone has gone through and done all of these reactions, and then from those reactions has determined the energy there. And so for sodium chloride, it's minus 411.2 kilojoules per mole. So you guys understand what a heat of formation is better, now that you've seen those videos? Or yeah, shame we can't do them in here. That'd be actually kind of crazy. That's way too high of a chance of explosion. Okay, so this one, if you, what did I do with my pencil? There should have these in the lab too. Oh, there's my Apple Pencil. I know there's at least one of these in the lab, but you also have these in the back of the book. But you know, like the stereotype for nerds always carrying lots of books around everywhere? That's probably where it came from, because if you're doing stuff, like, I mean, a book like this is extremely useful. Imagine I mean, now we just have MathLab, or I guess, did anyone use MathLab or Mathematica or something like that, some of these programs? I mean, or you have the internet. I mean, what's something crazy? What's the integral of the arctangent? I have it right here now. Integral of arctangent by parts. Oh. Right. And there's a video that explains how to do it on YouTube. Right? I mean, that's pretty cool, right? So I don't know how to do the integral of the arctangent. And now I have a video telling me how to do it. Right? That was before YouTube, this book is older than I am. It's pretty old. So if I wanted to figure out the integral of the arctangent if I had this book with me, I could do it. I could look it up. And then I could do it. And there's also logarithmic tables in this. So, but yeah, that's why I think all the stereotypes of the nerds came from, like skinny guys carrying lots of books, because you need them. You need the books. Without the internet, I mean, you need to carry all that stuff with you, and without a calculator. it depends on how far you are in math. Like the half angle formula for sine, to figure out the sine of 15 degrees is really hard. I mean, well, I guess if you know the formula, I hate to do that by hand, but I mean, nowadays if I want the sine of 15, I just put it in a calculator. I don't even, it's easy. But anyways, okay. Back to this stuff. Does anybody have any specific questions? I've gone to 3 groups, and I'm going to explain to the class, unless anyone want to ask something now. So you apply this equation. The heat of reaction, standard heat of reaction, is the sum of the products, heat of formation of the products, minus the sum of the moles of reactants, heat of formation of reactants. So the products are on the right side of the equation, and the reactants are on the left. So products, the delta H reaction, heat of formation of aluminum oxide, so that's a product, and there's one of them, plus 2 heat of formation of iron. It's an element, and this is standard state, so that's 0. But remember, iron can be solid, liquid, or gas. The standard state is a solid, so that's 0. And minus the heat of formation of the reactant aluminum, 2 times that, and plus the heat of formation of iron oxide, iron 3 oxide, and those aren't listed. I didn't list those because they're elements and they're 0, so it's the product minus the minus reactant, and you should get this selection A from that. Questions with how to do this? Okay, I know people said they wanted to do more problems, but I'm thinking about doing more problems right ahead of the test. So starting at least the conceptual part of quantum now, and then getting into, because there's a lot of problems that I think you'd like to see closer to the test. Okay, so moving on to quantum. There's 8. I like quantum. This is one of my favorite topics. Has anyone ever heard of Schrodinger's cat before? Yeah, Schrodinger's cat. So, well, if you ever get the chance, although again, I am a nerd, if you go to Stockholm, Sweden, if you go to the Nobel Museum, they have like recordings of all the Nobel Prize winners. They give like speeches, and like if you ever play this game, like who would you want to have lunch with? Like if you name like 3 people, living and dead, who would you want to have lunch with? I might pick Erwin Schrödinger for that one. He was really cool. He was a really cool guy, and his voice is electrifying. So if you ever hear his voice, he's completely electrifying. And because he got the Nobel Prize. So Schrödinger, he was a physicist, and he was really good at waves. And at the time, had a hard time figuring out the energy levels for the hydrogen atom. So they knew what the energy levels for the hydrogen atom were, but they couldn't figure out what it meant. And the legend is Schrodinger went and took a weekend off and thought about it and came up with his Schrodinger's wave equation. This is not it. That's the Heisenberg uncertainty principle. That's something different. Heisenberg, on the other hand, he's a prick. So he's someone I'd like to punch in the face. So he's not a very good person. Well, he was a Nazi, among other things. But he just wasn't a very kind person. Then again, I don't know how many kind. I guess there were a few kind Nazis. Who knows? But Schrodinger is really cool. As he was talking about he was figuring out something, and we'll talk about later. It's the wave-particle duality of electron and light. More in his case is electrons, which means if you expect an electron to act like a particle, it acts like a particle. If you expect an electron to act like a wave, it acts like a wave. And we'll talk about particle behavior and wave behavior later. And Schrodinger said, you know what? It's like I have a box. Be a bigger box than this. And this box is a cat. And inside the box, there's a machine that if I open the box, either the cat lives or the cat dies. And I can only find out if the cat lives or if it dies if I open the box. So, meaning I have a cat in here, and I open the box. I'm like, oh, live kitty. Like, ooh, dead kitty, kind of thing. And if I only figure out if the cat is living or dead by opening the box, what's the cat like when I don't open the box? And he's like, it's some sort of undead cat. It's like somewhere between living and dead. And that's okay in quantum mechanics. We call that a superposition, which we may not get to. So what is a superposition? Electrons can either be spin up or spin down. I guess I'm not flexible. Spin up or spin down. So, but what happens? But electrons are weird. They can be both spin up and spin down at the same time. That's called a superposition. And the problem with that is that we want to go into something called quantum computing. So right now our computers are based off of transistor logic, TTL, and they're based off of the 5-volt band gap of silicon. So meaning when it has no voltage behind it, doesn't conduct, that's a 0. And if it has 5 volts behind it, it does conduct electricity, that's called a 1. So that's our basis for binary. And we're thinking about using electron spins as binary. The problem is it going to be spin up, spin down, or it can be both at the same time, and then that ruins the math. It doesn't ruin the math, it just makes it much more complicated. But that's something that we're working on now. So we might have we do have quantum computers now, but they're not very advanced. So question, which door did you enter today? I came in that one. So, but if we were electrons, it'd be like, come on guys. We came in both at the same time. So electrons are weird, okay? So electrons, they can be in several different places at once. So we ourselves, we as big humans, we follow what's called classical mechanics. So classical mechanics, meaning I came in that door. Where quantum mechanics, you have uncertainty. And with uncertainty, when things are really tiny, you can do weird things, what we would consider weird, like walk in 2 doors at the same time. So later on, we'll talk about the 2-slit experiment. You can have an electron shooting towards 2 holes, and the electron can split and go through both holes at the same time. So we'll talk about that later. So I think this stuff is really cool. So I think this is, and I also remember when I was studying quantum mechanics, it's also when Harry Potter was really popular. So it did actually bring me a little bit of comfort. Like, I don't know, am I showing my age with you guys? Did you guys actually read Harry Potter when you were kids? Or, so I read it when I was in grad school. And it was actually, it was kind of comforting because I was learning quantum mechanics. Like, this makes no sense. Like, oh, it's magic. Oh. Okay. So with quantum, a lot of things we talk about light. We're going to talk about light and the interaction with light and matter. And light is a transverse wave. So a transverse wave is one where the displacement is perpendicular to the direction of the wave. So a light wave is going this way. Actually, I should back up. An ocean wave is a transverse wave. If an ocean wave is moving this way, and if you're in the ocean, where do you go? You go up and down. You are going perpendicular. Your motion is perpendicular to the direction of the wave. So, and we mentioned sound. Sound is a longitudinal wave. Sound, the motion of the air molecules is this way. The sound is moving the same direction that the displacement is. And so light and other forms of electromagnetic radiation is a transverse wave, and it's oscillating magnetic and electronic fields. Meaning, if the wave is going this way, the electronic field is going up and down. So, I mean, it's going to be going up and down like this. So, looking at it, but the wave is going this way, the electronic field is going up and down, up and down. Perpendicular to that is the magnetic field is going up and down this way. So meaning electronic field is going like this, magnetic field is going like this. And if you take physics, you can learn more about the difference between electronic field and magnetic field. So if you want the simplest definition, electronic fields cause charges to move towards you and away from you. Magnetic fields make them twist. If you want the simplest Cliff Notes version. Okay, and next thing with light, wavelength. So you can measure wavelength from crest to crest, trough to trough, or beginning to beginning. So meaning the wavelength is how long the wave is. So I mean here it's listed as how long it is there. You can measure it from here to here. You can measure it from here to here as well. So either way, it's how long the wave is. And also frequency, so wavelength is how long something is, and then frequency. What is your eating frequency? Like my eating frequency is I usually eat breakfast, lunch, dinner, usually a snack around 4 o'clock-ish. So today, though, I usually don't have lunch till 1:30 because that's when I meet my wife for lunch. So I probably get hungry around 11:30 or 12. So today I'll probably get a snack around 11:30 or 12. And then I'll have lunch at 1:30. And then we have dinner together around 5. So let's see here. And then I usually have a snack later on at night, too. So I guess my eating frequency today is 6 times a day. So, but typically it's 3 or 4. Right, so frequency is how often do you do something? What is your frequency for going to the gym? Mine is 4 days a week. I do chest and arms on Monday and Thursday, and back and arms on Tuesday and Friday. So 4 times a week is my frequency. Frequency is how often you do something. So frequency for wavelengths is how many times does a wavelength happen? And here is light. Red light. So red light is low frequency, long wavelength. And violet light is higher frequency, lower wavelength. If you were stuck in a storm and this is my boat. So you like my boat picture there. It's a triangle with another flag triangle. That's my boat. So which storm system is more dangerous? The red system on the top or the violet system on the bottom? Which one do you think is going to rock your world a little bit harder? The red or the violet? The violet, yes. Higher frequency radiation has more energy. So a photon, which we'll talk about later, which is the ultimate part, like an atom is an ultimate particle for an element, the photon of radiation of light, the higher frequency photons pack more of a punch. So, and that's another equation we'll talk about later. But it's funny, you can look at it, it's obvious. Some terms, why we do this in chemistry, I have no idea. Physics is much better. Physics uses F for frequency and L for wavelength. What do we do in chemistry? We use lambda for wavelength. Let's lowercase lambda. So that upside down y, this is lambda, or at least lowercase lambda, the Greek letter. And that funny v is nu. That is the frequency. So physics tells us the frequency times the wavelength is the speed. And that's also, in a way, it's kind of considered common sense. So how fast are you going? Well, it depends on how many times you're doing it and how long each of your steps are. So, I mean, it's like think of wavelengths instead of steps. So let's say my steps are, each of my steps are 1 meter long, and I do 1 per second. So this is a 1 meter a second motion. And let's say I do 5 steps, but 5 steps in a second. I'm going to shuffle my feet pretty hard. Put my ankles up to it. I sprained my ankle last week. So let's say I do 5 times in a second, but 20 centimeters each step. So, right? So that's, in that 1 second, I know I didn't go as far as my 1 meter step. But the idea is my frequency, but I had smaller steps. So, right? So 5 steps at 20 centimeters apiece versus 1 step in 1 second with 1 meter. So your speed is the number of times you do something times the wavelength per unit time. And for radiation, electromagnetic radiation, the frequency times the wavelength is equal to the speed of light. C is the speed of light. The speed of light is 3.0 times 10 to the 8 meters per second. So 300,000 kilometers a second. That's 186,000 miles a second. So speed of light, not surprisingly, is very fast. So it's very fast to us relative here on Earth. In the cosmic sense, speed of light is actually very slow. So for instance, it takes light about a little over 8 minutes to reach the surface of the sun to the Earth. So we're about a little over 8 light minutes away from the sun. Okay, and then speed, speed is just distance divided by time. So miles per hour, right? So if I'm going 55 miles an hour, that means in a period of 1 hour, I've traversed 55 miles. So the speed of light means that in 1 second, you've moved 300,000 kilometers. So that's or 186,000 miles. That's a lot of places to go. Okay, so hopefully this is common sense. We'll see if you can figure this out. What is the wavelength if the frequency is 4.62 times 10 to the 14 inverse seconds? So inverse seconds, the units for that is also known as hertz. Hz, hertz. So hertz is 1 over seconds. So you've ever heard the term hertz before. You've probably heard the term megahertz before, like 94.3 megahertz, for instance, or 99.9 megahertz. Those are radio stations, right? Those are the ones I listen to. So that means wavelength is going to be speed of light over the frequency, which is 3 times 10 to the 8th, all over 4.62 times 10 to the 14th. So 3 exponent 8 divided by 4.62 exponent 14. What is my add for today? Oh, it didn't give me an add. That's nice. Oh, I spoke too soon. So I got 6.49 times 10 to the minus 7 meters. So this is meters per second, and then this is 1/seconds. And then what you do is you multiply this by 10 to the 9, and you get 649 nanometers. So a lot of times for light, especially visible light and ultraviolet, we use nanometers is quite frequent. So this is probably a reddish orange color, actually. So I know I didn't even give you a chance to work on it, but that's the answer how to do that. Anybody have questions on how to do this? So people are squinting. Oh yeah, question.
Sorry, just why the 10 to the 9? Did you write 10 to the -9 up there?
So a nanometer, yeah, 10 to the minus 9. Okay, so let's do it this way. 6.49 times 10 to the minus 7 meters times I guess it would be 1 times 10 to the 9 nanometers per meter. Because like a centimeter is 10 to the minus 2 meters, right? So if I wanted to describe something in centimeters that I have meters, what do? I multiply by 100. So if I want to describe something in meters and nanometers, I need to multiply it by 1,000,000,000. 10 to the 9. Do you understand? Okay. All right, this is 0.1 meters. Okay, and I want to describe this in centimeters. I take 0.1 meters times 100 centimeters over a meter. So this is 10 centimeters, right? And now I have 6.49 times 10 to the minus 7 meters. I want to describe it in nanometers. And if nanometers is 10 to the minus 9, then it flips when you multiply it. So it's 10 to the 9 nanometers per meter. But do you understand the process? So wavelength times frequency is speed of light, or wavelength is speed of light over frequency. Speed of light over frequency, get that number. And if you change it from meters to nanometers, multiply it by 1,000,000,000. Questions? Okay. Next is the electromagnetic spectrum. So if you are a spectroscopist like me, I am a spectroscopist, and I dealt with, I don't do research anymore, but when I studied, I looked at especially infrared, visible and infrared. I looked how visible and infrared light interacted with matter. So everything in here does certain things with matter. And let me start over here on the left with low energy. So low energy and the speed of light. So we have low frequency but high wavelength. And over here, far left, we have radio waves. And what do we use radio waves for? We typically use them for communication. So AM radio, FM radio, television. Of course, we don't typically use television signals anymore. We usually just stream everything on the internet. So who knows, maybe television is going to stop broadcasting. And also cell phones. Cell phones are actually microwaves. They're the next on the list. But radio waves, we use them for communication. And what radio waves do is they change the magnetic properties of nuclei. So certain nuclei, most nuclei, act like magnets. Not all of them do, but most of them do. They act like magnets. And if you hit them with radio waves, the magnetic properties shift for nuclei. And we have a way of imaging something called nuclear magnetic resonance imaging. And people are afraid of the word nuclear, so we just call them magnetic resonance imaging, or MRI. And if you ever been in, has anyone ever had an MRI before? I've had 2. If you're inside of them, this is what they sound like. This is my lower back, in case you're wondering. At least it used to be. I don't know what it looks like now. But that is an image of my lower back. Here is my sacrum, my tailbone. There's L5 and L4. And notice, and here's L3. Notice that my discs at the time above there are nice and healthy. And over here, they're not so healthy. I have degenerative disc disease in my lower back. And over here, that's known as a protrusion. I had a piece of my disc sticking in my spinal cord. I can tell you it does not feel very good. So that hurts. So this, like I said, this is an image. And what is this image from? If you're in an MRI machine, this is what it sounds like. They're loud. It's cold and it's loud. And you hear this. It sounds like ka-chunk, ka-chunk, brr, brr, ka-chunk, ka-chunk, brr, brr. And what they're doing, they're taking magnets. So the ka-chunk, ka-chunk, they're moving magnets. And what the magnets do is they align all of your hydrogen molecules nuclei. So if the magnet's here, all of the hydrogen atoms are going to align, and then they blast you with radio waves. Your hydrogen atoms absorb the radio waves, and then they emit them. And they detect the emitted radio waves. And they do this in slices, and they slice you up into thin slices, and then they can bring up and they build images based off of those thin slices. So what this image is, it tells you where hydrogen are. If you ask the people, they say it's water, but it's not water, it's hydrogen. There is a lot of hydrogen in water, of course, but it'll detect the protons, and it doesn't matter if it's tied to muscle, fat, or water. It'll give you a signal all the same. And I'm not an expert, right? But I can tell you that this is different than that, is different from that, right? Of course, people are better at reading it than I am, but you can tell, this looks like a spinal cord, or at least, the vertebrae, and these look like discs, and there's something different between these two, except for right here, there's something funky, and then there's something here. So, from this, you can tell bones. You can tell other things like cartilage, and this is my spinal cord. So, it's different, right? So you can tell that based off of it. And what's nice about MRIs, they are completely safe. You can live in an MRI machine, and it will be completely fine. X-rays, though, can give you cancer. That's one thing. X-rays are bad. Okay, let's move on to microwaves. So what do microwaves do? We talked about this before with temperature. Microwaves makes molecules rotate. So if you have water molecule and you hit it with a microwave, it rotates, and then it collides into another water molecule, and it turns the rotational energy into translational energy. And microwaves, we use them for cell phones, we use them for radar, and we use them to cook things. So, and the inventor of the microwave oven was actually a radar technician, and he was working on a radar station, and he had a chocolate bar in his pocket, and as he was working on the radar station, the chocolate bar melted. And he goes, wow, I could use this as a cooking machine. So he did. He invented the microwave from that. And cell phones also use microwaves, and it doesn't seem like there's controversy anymore, but there was a long time people were worried if talking on your cell phone is going to give you cancer. And it doesn't. So cell phones and microwaves, they don't give you cancer. Later on, we'll talk about something called the photoelectric effect. There's not enough energy in microwave radiation to ionize something. So what is cancer? Cancer is a specific mutation. So it's a mutation that causes cells to grow out of control. And it comes from typically damage to DNA, and it's repaired incorrectly. So chemicals are very bad carcinogens. So radiation also it can be a carcinogen, specifically what are known as ionizing radiation. Ionizing radiation is ultraviolet and beyond, ultraviolet, X-ray, gamma ray. So all ionizing radiation can give you cancer. So sunlight has ultraviolet light. It can give you cancer. And specifically skin cancer. It only gets to so far. Microwaves, though, don't have enough energy. They cannot give you cancer. They can heat you, but I mean, that's not all it can do. Let's do this the other way around. What would happen if microwaves did cause cancer? And who would have tons of cancer if microwaves cause cancer? Well, it depends. I mean, if you live out in the Amazon, then you'd be fine, or in like the Serengeti. Yeah, I mean, anyone that worked around an airport, anyone that worked on a Navy ship, and you've seen Navy ships, they have radars, right? I mean, they're getting blasted with microwaves. Anyone who works like, is it called the Ajax fighters or whatever, the surveillance planes? They have big radar stations on them. They'd all be dead. What? AWACS, sorry. Yes, AWACS. I mean, they're getting blasted. That guy that invented the microwave oven, I mean, it was so much microwaves, it melted chocolate in his pocket. You know, did he get cancer? Well, I don't think he did, but I mean, I'm not entirely sure about that. But I mean, he lived, as far as I know, a long life. So microwaves don't cause you cancer. Same thing. So infrared, what infrared does, it makes molecules vibrate. So if this is water, here's water, and you can either do, this is called a symmetric stretch, this is called an asymmetric stretch, this is called a bending mode. So you can learn about this stuff later on in more chemistry classes. But it makes molecules vibrate. So if you hit infrared light, like on like your shirt or something like that, your shirt is, mine at least is cotton. Cotton is a long chain. It'll make the chain vibrate. All these molecules will be vibrating on the chain. So a hot shirt is going to be the chains vibrating more, at least with infrared light. So that's what infrared light does. So if you feel, and you can feel it. So you go to a fire, like, I feel the heat. You're feeling the infrared light. It's a way for heat transfer. And then we get to visible light. So what does visible light do? Visible light causes electrons to jump up and down in energy levels. So at least absorbing light causes them to jump up. When they go back down, they emit light. And red light, so is around 700 nanometers. This is low energy. Violet light is 400 nanometers. That's higher energy. So we as humans, most humans can see down to about 800 nanometers. But most can see well between 700 and 400. So if you look at this chart here, this is my own drawing. Our eyes have two different types of light-sensitive cells, rods and cones. Rods just tell light intensity. Cones are color sensitive, and we have three colors. At least most people have three colors. So if you have two, that's known as color blindness. Two or less is color blindness. And you can even have four, that's known as a tetrachrome. The species that's really good with colors are mantis shrimp. They have 11. But they don't have the brains to interpret it. So humans, we see very, very well. Of all the species, in my opinion, I think humans see the best out of any species. So eagles can see more finely than we can, but they do it as far as hunting. So they can see prey really high up. So the raptors have really good eyesight in that regards. But they have tiny brains. Humans, we can't see as well as the raptors in terms of resolution, but we have a bigger brain, so we can interpret the visual input much more effectively. And but other animals, they don't see as well as we do. I mean, like dogs and cats, they just do not see as well as humans do. So to us, vision is a very rich sense. Whereas cats and dogs have much better sense of smell than we do. To them, smell is much more rich than vision. But for us humans, most humans have three cones, and by intensity of the effectiveness, we have red, green, and blue cones. So we see 3 colors, and then the combination of those signals is how our brain interprets the colors. And if you could pick one color, which one is just smacks you in the face bright? If you had to pick one color, what would it be? Green, yeah. Specifically that fluorescent green, that lime green, fluorescent green color, right? That is the color that we see the best. Like you ever see sometimes, I mean, they painted fire trucks now. They used to paint fire trucks red. Then they painted that fluorescent green color because we see it the best. We see that color the best. And that's also the highest frequency that comes from the sun. So the sun peaks at a lime green color. So our sun is not a yellow star, it's actually a green star. So if you want to go by colors. So although the sun looks white to our eyes at least, but if we were spectrometers, it would look green, or a lime green color. And we humans, we also have a hard time distinguishing between the colors purple and violet. Does anybody know what purple is and what violet is? So violet is light with a wavelength of 400 nanometers. How do you get purple? You mix red and blue. So for us humans, we have a signal. Our red signal actually absorbs in the blue a little bit. So for us humans, we have no way of differentiating. We cannot differentiate between a violet photon or red and blue. We have no way of telling the difference. It looks the same to us. So, but I mean, a spectrometer can. But I mean, humans, we're not spectrometers. Our vision, we're more analog in terms of our vision. We take our senses and like, okay, are we in trouble? Can I eat it? You know, kind of thing. Is that going to eat me, or is it all good? Right? That's kind of what a lot of our instincts are. So, but I always thought that was interesting. I should have brought my lasers in because they're all the same energy, but the green one looks so bright. Okay, so but really the colors here, at least for us humans, it is just like an orange. Orange is going to be right here. So our brain knows that a certain amount of green with a certain amount of red gives us the orange photon. So then our brains can interpret the difference between orange and yellow. But it's really just the relative input from 3 different, for most people, 3 different signals and colors. And they're not the same for everybody. Some people have a little difference. Some people can see beyond. Some people can see in the ultraviolet, especially people that have their cataracts removed. So one of my favorite artists is Pierre-Auguste Renoir. He had his cataracts removed and he painted differently. And people think it's because he could now see in the ultraviolet. He was painting what he could see in the ultraviolet. And I can't see in the ultraviolet. I can see to about 380 nanometers. So something about 380 nanometers, to me it looks like really faint lilac, like a really, really light violet. And most people can see down to about 800. To me, 800 looks like dark brick red, kind of like this color. So, and I know this also because there's a laser, a Thai sapphire laser, pumps out at about 820 nanometers, and most people can see it. But you don't see it very well. That's one thing, is you don't see this color very well. It looks really kind of a faint brick red, and to my eyes at least. So, and I always have to be careful when I talk to people. People like, when we do flame test lab, and like, what color is that? And I'm like, well, I don't know. What do you perceive it as? Like, looks purple to me. I'm like, all right, you know, however you want to. I mean, I can't tell you what your eyes do. You know, it's like, and I always wondered about that. Like, I mean, I see this as red. Does this look green to you? Well, I would call green. I mean, do we really perceive everything the same? I mean, it's one thing we actually don't know. So, I don't know. Kind of cool. Okay, moving on. Ultraviolet. So, and look at the names. So, infrared, less than red. Ultraviolet, beyond violet. Ultraviolet. Now, ultraviolet is dangerous because it's ionizing radiation. So what does a jumping bean do? It jumps. What does a kicking mule do? It kicks. What does ionizing radiation do? It ionizes. What does it mean to ionize? It means you create charged particles. So in this case, how does it create charged particles? It rips off electrons. So ultraviolet light rips off electrons. Ultraviolet light specifically rips off surface electrons, so the electrons that are on the outside of the atoms. And X-rays rip off electrons in the core, in the inside of the atoms. And then gamma rays, they rip off all electrons, and they also, the same thing with colors. So colors are electron energy levels here. Gamma rays are colors for energy levels in nuclei. So gamma rays, they deal with nuclear events, and they're very, very high energy. So ultraviolet light will only hit the surface. So ultraviolet light can give you skin cancer, specifically UVB. So UV is divided up into 3 color ranges. I mean, we don't perceive them, but low energy ultraviolet is UVA, medium energy is UVB, high energy is UVC, and they can actually go beyond that. There's something called vacuum ultraviolet. That's closer to X-rays. So UVA light is the primary cause of wrinkles. So what are wrinkles? It's scarring of your dermal layers, your underneath layers of your skin. And then your epidermis, your outside layer, goes over those folds. And how do you get wrinkles? You can be born with them. I've got wrinkles here that I was born with. Everyone in my family has it too. Also by repetitive motion. Like if you see someone, if you see like an old person, you're kind of like, is that person live a happy life or a sad life? You can kind of tell. Like if they smile a lot, they have wrinkles this way. If they have frowny faces all the time, they have wrinkles another way, right? So you can kind of tell that, how often the person smiles or frowns. But where a lot of the damage comes from is from the sun. The sun, the UVA light scars the lower layers of skin, and that's the primary cause of wrinkles. So how do you avoid getting wrinkles that way? Sunscreen, 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 sunscreen. Or just don't go out in the sun. And UVB light, that's what causes skin cancer. It's also what causes you to get tan. So SPF, the sun protection factor, is only for UVB. So if you see something that says broad spectrum, that'll cover UVA as well. It doesn't cover UVA as well as UVB, just so you know. But UVB, we need it. So us humans, we are slightly photosynthetic. We take cholesterol and we change it to calciferol, which is provitamin D3. So, and then our body stores it. So we actually can get we can manufacture vitamin D ourselves from the sun. And not a big deal for us in Hawaii, but in other places, a lot of people live in Iceland or something like that where it gets dark, or out Alaska. They love to have these lamps that put off ultraviolet light. It makes them feel, it gets rid of seasonal depression. And seasonal depression is a real thing. I used to live in Wisconsin. Not seeing the sun for a while. It can affect you after a while. And okay, X-rays. X-rays go for core electrons. X-rays can give you surface electrons. It can rip off surface electrons too. So dentists, now we stigmatize radiation. I mean, it should be stigmatized. But have you noticed, when you're at the dentist, they always tell you, okay, take this thing. I was just at the dentist last week, actually. They told me to take the film and stick it there, and all right, and they retreat and they run somewhere else, and then they turn on the X-ray machine. Dentists used to do that themselves. They would hold the things, like the film, and then have the X-rays. What happened was they would have manky fingers. So dentists, I hate the dentist already. Not that they're all nice people, but I don't like it when they scrape my teeth. That's not a pleasant experience. And if they were scraping my teeth with scaly-looking fingers, I'd be even worse, right? I'm like, ugh. You want to put that in my mouth? Right. So, and then gamma rays, even high energy. These ionize everything, and they come from nuclear events. So, not just bombs. So whenever there's a decay series, we haven't talked about this we won't until next semester. Anytime there's an alpha, beta emission, there's a gamma ray as well. So gamma ray is just high energy photon. Everyone's packing up. Is it time to shut up? Oh yeah, 1 minute left. All righty, anybody have any questions? Yeah, question. That's radio waves. Yeah, radio or microwave. They don't like it when I ask questions at the airport. So they say millimeter. It says millimeter wave. So that would be right around here. Yeah. So actually, let me say by this, then millimeter would put us closer to infrared then. Yeah. Yeah, I get yelled at a lot whenever I go to the airports and ask them what they're doing. Like, we're not going to tell you, sir.